Hello, welcome to your favorite integrated science show on Teacher and You Joy Learning. I am your facilitator and I'm called George Lokko from St. Mary's Senior High. Today, we started a bit late and I want to apologize because we had some technical challenges. So our time couldn't be exactly at 12 o'clock as scheduled. I shall be introducing you to a wonderful topic in integrated science called the mole concept. And today we'll attempt to address some portions of the mole concept. To help us do this, let us look at our learning objectives for the day. So at the end of this lesson, you, my cherished students, will be able to define the mole, Avogadro's constant, define the carbon-12 scale, define the relative atomic mass, use the relative atomic mass to determine relative molecular masses, define the mole, and Avogadro's constant repeated. So we start right away with the mole concept. The objects we see around are called macromolecules or macro objects. So your friend, your brother, your uncle is a macro object, meaning that it's a huge molecule or object you can easily touch, feel it, and also weigh it. So you as an individual, you can easily stand on a scale and measure your mass. I weigh 85 kilograms. I don't know how much you weigh. So very soon I'll be calling people to tell us how much they weigh. Now, in the case of the atoms, those tiny particles that we cannot readily see, the scales that we use at home cannot be used to measure their masses. So a new concept has been designed to help us determine their physical properties in terms of their mass, densities, and any other physical property you can imagine. That part of chemistry or integrated science that has been designed to address the physical problems or the physical properties or characteristics of micro objects like the atoms, the ions, and the molecules is what we call the mole concept. So it means that the mole concept is just an idea that has been developed and it has really helped scientists all over the world to address the physical properties of tiny particles, what we call the micro objects. You and I, who are macro objects, can easily be weighed on a scale. So it means that we also have to find a scale that will help us determine the masses of these tiny particles. And therefore, that tiny particle can only be weighed when we devise a scale. Remember, any scale that we use in measuring mass must have a standard unit, and the standard unit must be smaller than the particle in question. So when you go and stand on a scale, the mass that you get is a comparative mass of yours and a very tiny particle standard, all right, in the measuring equipment, what you call the standard unit. In the case of the mole concept, it means we have to devise a scale that will help us measure the mass of a very tiny particle like the atom, the element, or the molecule. And that means that that scale must also be equally small. That scale must also be equally small. The scale that we use in determining the masses of these tiny particles is what we call the carbon-12 scale. So in order to determine the physical properties of these atoms, ions, and molecules, what we call the microparticles, the carbon-12 scale has been designed. And therefore, we can say confidently that the mole concept is basically based on the carbon-12 scale. So without the carbon-12 scale, we cannot measure the masses of these atoms, ions, molecules, and any other tiny particle you can imagine. Let us look at the carbon-12 scale. I mentioned earlier that any scale that we use in measuring the masses of objects must have a standard unit smaller than the object in question. So we as humans, when we stand on the scale, there is a tiny standard unit in the scale, the gram or the kilogram, which we use in the comparison. What about the carbon-12 scale? Now, to do the measurement, we use carbon-12 scale. Question, why do we use carbon-12 scale and not any other scale? Now we have to appreciate the fact that there are other skills in chemistry or science for that matter, but carbon-12 has been chosen for a reason. Carbon-12 scale has been chosen because it is reference to the carbon-12 isotope. Remember from JHS, we were told that isotopes are atoms of the same element having the same atomic number but different mass numbers. I'm sure you remember. So if these are isotopes, that means that we can also use other forms of isotopes of other elements. But the carbon-12 has been chosen because it is abundant. It's everywhere, so we can easily use it. And carbon-12 again because it has equal distribution of particles in the nucleus. Let us digress a little and talk about atoms, particles in the atom. We know that in the atom, we have particles in the form of the protons in the nucleus, the neutrons in the nucleus, and the electrons occupying stationary states around the nucleus. Relatively, the electrons are negligible in terms of mass. So when you take an atom and you weigh it like the carbon-12, the mass that you get is basically coming from the nucleus. And that means that we can also use carbon-12 as our point of study. Let us continue further and see what we can do with this. So we say that the carbon-12 scale is the mass reference scale in which one atom, the carbon-12 isotope, is taken to have 12 units of mass. So it means that there are 12 particles in the nucleus of the carbon-12 isotope. Then we have protons, and then we have neutrons. There are 6 protons, and we have 6 neutrons. How did we get this? Carbon has an atomic number 6, but the carbon-12 isotope has a mass number of 12. And we know that mass number is the sum of the number of protons and neutrons in the nucleus of the atom. So if we take the isotope carbon-12 and we subtract the protons, which are 6, from the mass number, which is 12, we are also going to get 6. So it means that we have equal distribution of particles in the nucleus of the carbon-12 isotope. Here, we say that it is a reference scale having 12 units, but each unit represents a particle in the nucleus of the carbon-12 isotope. So it is a scale of division, which each division representing a particle in the nucleus of the carbon-12 scale. Now, the unit of measurement on the carbon-12 scale is the grams. All right, so how do we get the unit? How do we get the smallest unit? We take the mass of the carbon-12 isotope and then we divide it by 12 because we have 12 particles in the nucleus. So if the mass is, say, X, the atom weighs X, and you want to find the mass of the proton, just divide the mass of the atom there by 12 because there are 12 particles, and the electron doesn't weigh anything compared to the protons and the neutrons in the nucleus. Now, when you do that, that small unit that you get is what we call the atomic mass unit. So the atomic mass unit is simply the mass of one particle in the nucleus of the carbon-12 isotope. In terms of value, we say that it is 112, the mass of one atom of the carbon-12 isotope. So if I take, for example, this is my phone, and this is the carbon-12 isotope, and it weighs, say, X grams, then if I want to find the mass of a particle in the nucleus of this phone, which is a particle, I have to divide the mass, which is X, by 12 because we have 12 particles in the nucleus. I hope we are following. So that's mass, that average mass that we shall get when we divide the mass of the carbon-12 by 12 is what we call the atomic mass unit. So the question is, what do we use that atomic mass unit for? Remember, we said if you step on the scale, there's a small unit there that you're comparing yourself to. So similarly, with the carbon-12 scale also, the small unit in the scale is the atomic mass unit, or 112, the mass of one atom of the carbon-12 isotope. So when we put an object on the carbon-12 scale, we are comparing it to one atomic mass unit, or 112, the mass of one atom of the carbon-12 isotope. When we take the average mass of the isotopes of an element, remember every element has isotopes with the exception of fluorine and gold. Now, if we take the average mass of these elements and we compare it to a particle in the nucleus of the carbon-12 isotope, then we are going to get what we call the relative atomic mass. If you pick just the atom and drop it on the scale, you get the average mass of that atom. But if you find the average masses of the isotopes of that element and compare it to one atomic mass unit, the value that you get is what we call the relative atomic mass. So we say that the relative atomic mass, by definition, is the weighted average of the masses of the atoms of the element compared to 1/12 the mass of one atom of the carbon-12 isotope. Now, the relative atomic mass is denoted by AR. Mathematically, we can also express it as AR equals the weighted average mass of atoms of the element, all divided by 1/12 the mass of one atom of the carbon-12 isotope. I hope you are following this story. Now, let me go back and then show you something. The average mass of the atoms of the element, if we are to measure, should give us grams, isn't it? Because the SI unit of mass is actually kilogram. But because we deal with small substances, we measure it in grams. So it means that the weighted average mass of atoms of the element should have the unit of what? Grams. And also the one atomic mass unit should also have the unit of grams. So if we divide the weighted average mass by the 1/12, the mass of one atom of the carbon-12 isotope, the units should cancel. The unit should cancel. So we say that relative atomic mass does not have a unit. That is why if you are doing your calculations in the mole concept for relative atomic mass and relative molecular masses, you don't put unit there because it is a weighted average mass and it is a comparison of masses. So the units will cancel. So we say that it has no unit because it is a comparison of masses. It is also not necessarily a whole number because it is a weighted average mass. Why do we say that it is necessarily not a whole number? If you have 3 numbers or 4 numbers and you find the average, if the numbers are even, you may get even number. But if you have an even and an odd number, then you will not get necessarily a whole number. You may get a decimal fraction, all right? So if you find the relative atomic mass of an element, you don't always get a whole number, because you are finding the average mass first and comparing it to one atomic mass in the carbon-12 scale. Interestingly, because isotopes of elements are unique in terms of their mass numbers and proton numbers, we can also say that the elements on the periodic table are all unique. They have different numbers of protons and different numbers of neutrons, giving them different mass numbers. And as a result of that, we shall have unique relative atomic masses for all the elements on the periodic table. So on the periodic table, we can therefore say that the elements have unique relative atomic masses, and hence we can use that to do our calculations. So every element has its own relative atomic mass, which is unique to it only. You don't have any other element sharing that. And the relative atomic mass of some elements are shown below. So below this page, I'll display for you to look at the average masses of some of the elements. By now, if you are in SHS1 or SHS2, I believe that you know the elements from 1 up to at least 40 or from 1 up to 50. If you are still handling the 1 up to 20, then you are still in JHS. You should go back and then increase the numbers. So let us look at some of the atoms of the element, their atomic numbers, and their relative atomic mass. Please, the relative atomic masses that we are giving you are not supposed to be memorized. If you are supposed to be using it in an exam or in a question, it will be supplied. But we have to explain where we got it from. That is why we are explaining how they came about. Now, if you look at this table, on your left-hand side, we have atomic number. The next column, we have name of the element. We have chemical symbols, and then the relative atomic mass. So for example, if I pick hydrogen, whose atomic number is 1, with a chemical symbol H, and I find the average mass of the isotopes of hydrogen. There are 3 isotopes of hydrogen, and you compare it to 1 atomic mass unit, you get the value 1. So it means that hydrogen is 1 times heavier than the particle in the nucleus of the carbon-12 isotope. Now, for the second one, which is helium, with atomic number 2, you'll notice that it has a symbol He, but the mass number, the relative atomic mass, is 4. So it means that helium is 4 times heavier than that simple unit in the carbon-12 scale. I hope you understand. Further, we can move on to lithium, whose relative atomic mass is 7. Beryllium, the relative atomic mass is 9. And then boron, the relative atomic mass being 11. Like I said, please don't memorize these values, because for every question, you'll be given the value to work with. carbon, nitrogen, oxygen, fluorine, neon also have their chemical symbols, which I know you are familiar with. But like I said, if you don't know the first 20, please, even if you know the first 20 by now, you should shift to first 30, first 40, or first 50. If you're a science student, all the 118 is required of you to be known. So carbon has atomic number 6. Its relative atomic mass is 12. Nitrogen, atomic number 7, and the relative atomic mass is 14. So let us see if there can be a correlation. Look at the atomic number and look at the relative atomic mass. You see that it is almost double. If you check, it's about almost double. Have you seen it? So you see that carbon is 6, the relative atomic mass is 12. Nitrogen is 14, nitrogen is 7, the relative atomic number is 14. Oxygen is 8, the relative atomic number is 16. Fluorine is 9, and the relative atomic mass is 19, a little more than the atomic mass there because of the weighted average mass I explained earlier. So neon also has this atomic mass as 20. Okay, so we move further. We have sulfur, chlorine, argon, potassium, and calcium. They all have the atomic numbers 16, 17, 18, and 19. Our screen is shifting, but we'll continue. Okay, so like I said, we have sulfur, chlorine, argon, potassium, and calcium with atomic numbers 16, 17, 18, 19, and 20, with the chemical symbols S, Cl, capital AR, capital K, and then capital C, small a. Their relative atomic masses are displayed on the right-hand side. So let us look at them carefully. Sulfur is 32, chlorine is 35.5, argon is 40, potassium is 39, and calcium is 40. When you go into the actual calculations of the relative atomic masses, you will not get whole numbers like this. These are average masses, and some of them we have rounded them up to the nearest whole number. But you are going to get very long decimal fraction if you go into the detailed calculation. So we'll continue. Those of us who are not familiar with the next set of elements, then we will have to go to scandium. So the element that starts from calcium is scandium, and it ends with zinc as 30. So let's go through them quickly. So scandium has a chemical symbol Sc. The relative atomic mass is 45. Titanium or titanium has a chemical symbol Ti, capital T, small I, with a relative atomic mass 48. So we are going through vanadium, chromium, manganese, and their values are displayed on the right-hand side. Iron, cobalt, nickel, copper, and zinc are the next set of elements on the periodic table. So here we have considered the first 30 elements. Iron, cobalt, nickel, copper, and zinc are the next set of 5 elements after the 25th element, with their chemical symbols Fe, capital Co, capital Ni, capital Cu, and then capital Zn. And their relative atomic masses are displayed on the right-hand side of our table. At this point, I'll pause a little and then ask 1 or 2 questions. We have our friend Godwin Nanakwesi Apia. So this question goes to you. Tell us the chemical symbol for chromium. What is the chemical symbol for chromium? Gordon, we can't hear you. Well, we can't hear Gordon, so we shall continue. I don't know whether Elliot will help us. Elliot, what is the chemical symbol for chromium? Elliot, what's the chemical symbol?
Sc.
Well, Sc is scandium.
Chromium is Cr.
Chromium is Cr. Thank you very much. So, friends, chromium is Cr. We have to know the chemical symbol of some of these elements. Now, these values are used to calculate the masses of molecules containing two or more of the combination of the elements above. So we are now looking at significance of the masses we have been given. These values, these plenty values they give us, what are we supposed to use it for? That is what we are going to look at next. So if, for example, we have two people, A and B, so that A weighs 5 kilograms and then B weighs 30 kilograms, and we put the two on the scale, how much should they weigh? I'll say it again. Two people, the first one is A, the second one is B. These are their names. A weighs 5 kilograms and then B weighs 30 kilograms. Now we put the two of them on a scale. How much should they weigh? Elbra, can you be of help? We have two people, one weighs 5 kilograms, the other one 35 kilograms. Now, if the two of them steps on the scale at the same time, what should be their collective mass? Ebra, we are waiting. Well, we lost Ebra, right? Well, as this show is going on, I have to let you know that you should invite all your friends onto the platform, all right, so that we can have a very nice interaction. Now, as questions are posed or you have a question and you want to answer it, you can forward it to joylearningtv@myjoyonline.com. Joylearningtv at myjoyonline.com. Now, if a person weighs 5 kilograms and another 30 kilograms, and we put them together and they step on the scale, the collective mass should be the sum of the masses of the two, isn't it? So it's going to be 35 kilograms. So if you and your brother, you weigh 35, you weigh 30 kilograms, and your brother weighs 5 kilograms, and you carry your brother and step on the scale should read 35. That is exactly what we use the values that we've just shown you to do. They are used in calculating the masses of atoms when they come together to form compounds. Remember, in nature, atoms combine to form compounds, and they do that in simple whole number ratio, as postulated by John Dalton. So we say that these values are used to calculate the masses of molecules containing two or more of the combination above. So the values that we have above are going to be used extensively by us to do series of calculations and to use them to do other applications. What do we use the values for? So let us look at the application of the values we just gave you, the applications of the relative atomic mass. Now we said two or more atoms can combine to form a compound. Now, when you are able to get a compound, you should be able to work the mass of that compound as well. So what you have to do is you take the whole compound, put it on the carbon-12 scale, and that gives you the mass. But remember, it can also be calculated easily, all right, if you know the masses of the various atoms of the elements present there. So if you have a compound, let's say A, B, and C, and you know the masses of A, B, and C differently, then you can put them together if you know the numbers of A and B that combine to form the compound. We'll be looking at it as we move further. And that molecular formula that you get, if you determine the mass, is what we call the relative molecular mass. The relative molecular mass. So we say that the relative molecular mass is the average mass of a molecule compared to 1/12, the mass of one atom of the carbon-12 isotope. The weighted average mass of one molecule of a compound compared to 1/12, the mass of one atom of the carbon-12 isotope. Relative molecular mass is denoted by Mr. It is denoted by Mr. Many years ago, relative atomic mass and relative molecular mass had their representation. Relative atomic mass, for example, was denoted by RAM. RAM, that will sound a RAM, all right? In those days, computer was not around, so we were using it happily. But now we've moved to AR because now we have RAM. Apart from a chip, it can be a random access memory associated with the computer. So we no longer use that. And again, we have the RMM. So if you are using old books, you see RMM, which is the relative molecular mass, all right? And that again has its own denotation and representation in computer. So these days we have stopped using them. We are using the MR and the AR. So by definition, we said the relative molecular mass is the weighted average mass of a molecule of a compound compared to 112, the mass of one atom of the carbon-12 isotope. Mathematically, we can also express it as shown on your screen. The weighted average masses of the molecules of a compound, all divided by 112, the mass of one atom of the carbon-12 isotope. So we take the weighted average mass and then you divide it by 112, the mass of one atom of the carbon-12 isotope. It can also be calculated as the sum of the masses of all atoms of elements present in the molecule. So if you have a molecule made up of, for example, water, in the case of water, we have 2 atoms of hydrogen and an atom of oxygen. So if you want to find the mass of one molecule of water, since there are 2 hydrogen atoms and 1 oxygen atom, you add the masses of the 2 hydrogen atoms to the mass of 1 oxygen atom. I hope you are following. So it is calculated as the sum of the masses of all atoms of elements present in the molecule. The average mass of an atom of element we said is called the atomic mass, of which has been supplied in the table above. So we are going to be using these values to work. Again, the relative molecular mass does not have a unit. It doesn't have a unit. Remember, it is drawn from the relative atomic mass, and the relative atomic mass doesn't have a unit because it is a comparison of masses. So similarly, relative molecular mass also does not have a unit, and it is also not necessarily a whole number. So take note of that. Like I said earlier, you are not supposed to memorize the relative atomic mass values above. You are not supposed to be given for every question you have to be supplied. So if you've come across a question and you don't have the relative atomic mass, you can refer to a book and use the values there to calculate. If it's an exam and you are not given, you raise your hand and call for the values to be given because you are not supposed to memorize it. So let's take an example. So for example, consider that it's a hypothetical molecule. It means it's not real. Consider the hypothetical molecule A3, B5, C2. So let's note it down. A3, B5, and C2. The relative molecular mass of the compound can be calculated as shown. Here, we use MR to represent the relative molecular mass. We're having some small technical challenge, but we'll still continue. We use MR to represent relative molecular mass, and then the relative molecular mass can be calculated as shown. I'm getting a pointer so that we can, I'm having some hand, so it has come now. The relative molecular mass here is the MR. You always have to put into bracket or parenthesis the chemical formula of the compound you are working with. So the MR here means it's a language you are communicating to somebody, relative molecular mass. But relative molecular mass of what? Of the compound A3, B5, C2. A3, B5, C2. And to get the relative molecular mass of this compound, it means we have to add the masses of all the A together to the masses of all the B together to the masses of all the C together. It's similar to you and your brother's story. You weighed 35. Your little brother was 5 kilograms. When you step on the scale, the total mass there will be the sum of the masses of you and your little brother. So it's the same thing. We have to add the masses of all these elements, and then we compute it. Since there are 3 of the A's here, I'll multiply 3 by the mass of 1A. Remember, the average mass of 1A is what we call the relative molecular mass. So the relative molecular mass is what you are showing on your screen here, the capital A, small r, and then you put into parentheses the A. And then you add it to 5 times that of B, because in the compound there are 5 of the B's. If there were to be 2 of the B's, then I would have multiplied with the 2 by the mass of 1. I hope you understand. Then we move further. We are going to multiply 2 by the mass of 1 of the C, because we have 2 C's. That's why we are multiplying 2 by the mass of the C. So to get the relative molecular mass of a compound, You add the masses of all the atoms present in the compound. If the element is not there or the atom is not there, don't force it. It's not part of the molecule. And then you work with what is only there. At this point, I'll pause for you to ask questions. I'll pause for you to ask questions. And if you don't have a question, then we can move on to our example. For question time, ask your questions. Nobody is asking. So can we continue? Very well, let's continue. So let's take an example. Calculate the relative molecular masses of the following compounds. Calculate the relative molecular masses of the following compounds. What are the compounds? We have water, ammonia, sodium triacylcarbonate 4, or what we call sodium carbonate or baking powder. And then we have the sulfuric acid or tetraoxo sulfate 6. So these are the compounds we have on our screen. Water, ammonia, sodium triacylcarbonate 4, tetraoxo sulfate 6 acid. So take note of them and we'll do them together. Then the next set of questions, we have what we call the sodium thiosulfate hexahydrate. All right, sodium thiosulfate hexahydrate. So take note of that also. And then we'll also have the copper 2 tetraoxo sulfate 6 pentahydrate. Copper 2 tetraoxo sulfate 6 pentahydrate. When we get to the nomenclature of these compounds, I'll show you it's not anything difficult. Everybody can do it. So we have CuSO4, and then you have 10 molecules of water. Now use the values from the table above to answer the question. So I'll give you some time, work it out, and then you all present your presentation. I'll be calling one by one. Please don't run away. We want to be online. We want to have fun. So don't run away. Solve the questions and let's go. So we have ammonia, we have water. So apart from the water, remember we have sodium carbonate, Na2CO3. So let me go to the first page so that people can easily refer to it. Try and solve it on your own. Solve it somewhere so that when we are working it, you can also follow and ask questions why you didn't get it correct or contribute to the class why we should ask something. So for a quick reference, hydrogen is 1. The relative atomic mass of hydrogen is 1. Oxygen is 16. Nitrogen is 14. Well, carbon, no, we have sodium here. Sodium is 23. Carbon is 12. Sulfur is 32. I'll go over it again. Hydrogen is 1. You need the values to work. So if you don't have it readily, I'm putting it so that you can write it and use to calculate. Hydrogen is 1. Oxygen is 16. Nitrogen is 14. Sodium is 23. Carbon is 12. Sulfur is 32. So in the next 2 minutes, let's see your presentation. Then we'll move on together to the solution. All of us will do it together. So I'm okay. So welcome back. I'm not going to call anybody to present his or her work. So those of you who ran away from the platform, please come back. I'm going to solve it. I gave you time to solve it so you can compare it to your answer. Let us look at how we'll go by the presentation of the answer in these questions. So the first one, we were supposed to determine the molecular mass. We were supposed... Hello. Somebody is talking. Okay, so if we can't hear you, otherwise you can unmute so that we move on. Okay. So the...
Can you hear me?
Yes, I can hear you. Go ahead.
Please.
So mention your name, your school, or where you are calling from, and then you ask your question.
I complete Kukroma Greek Senior High School 2020.
Okay.
I've completed.
Your line is breaking. The
internet please, I saw it as well. Sorry.
Okay, so you got the same answer, right?
Please, I saw it.
Okay, but did you get the same answer as what we have here? All right. So we thank our friend.
Yeah, it's the first one. I got the team.
Yeah, okay. So you've done very well. Congratulations. So I want to explain it, then we move on to the next example. Okay, so you pause. Let's finish this. Then you can call it. You are calling again. So unmute your mic for now. Okay. So water with the chemical formula H2O has 2 atoms of hydrogen and an atom of oxygen. With this, it means I have to multiply 2 by the average mass of 1 hydrogen, and then I add it to 1 by the mass of oxygen. So that is the expression we have here. The expression we have there. Today, our machines are giving us a big challenge. So we will have the expression we have here. So we are going to multiply the values we have there. So here we multiply the 2 by the relative atomic mass of hydrogen, and we add it to 1 by the relative atomic mass of oxygen, because in this compound we have 2 atoms of hydrogen and an atom of oxygen. Now the next step of the expression should have the values. We'll multiply therefore 2 by the mass of hydrogen. Remember we said the value there was 1. And then we add it to 1 by the mass of what? 16. Because we said the relative atomic mass of hydrogen is 16. So if you evaluate it further, you get 2 times 1 giving you 2 plus 1 times 16 giving us 16. The sum of which will be 18. Now if you check, I didn't put any unit there because we said relative molecular mass does not have a unit. Now we move on to the next one. That of the ammonia. The chemical formula for ammonia is NH3. NH3, meaning there are 3 hydrogen atoms and then an atom of what? Nitrogen. So the expression again is similar to the water. Since I have 1 nitrogen, I multiply 1 by the average mass of nitrogen, and I add it to 3 by the average mass of hydrogen. Now if you substitute the values into the expression above, you therefore get 1 times 14, because the average mass of nitrogen is 14. And then 3 times that of hydrogen, because hydrogen is 1, which will result in 1 times 14 giving us 14, and then 3 times 1 giving us 3, the sum of which will give us 70. So compare it to your calculation. Sodium trioxocarbonate form. People call it baking powder, baking soda, washing soda. They have so many nicknames. Now, in the case of this compound, sodium is 23, I mentioned, carbon is 12, and then oxygen is 16. I am going to multiply 2 by the mass of sodium, because we have 2 sodium atoms in the compound. And then we also add it to 1 by the mass of 1 carbon, because in the compound again, there was only one atom. Then we add the resultant to 3 by the atomic mass of oxygen. Now, if we substitute values into the expression we've generated, then we'll get 2 times 23, because 23 is the average mass of sodium, and then 1 by 12, because 12 is the average mass of carbon. And then again, we have 3 times 16, because 16 is the average mass of oxygen. This will result in 46 plus 12 plus 48, because 2 times 23 is 46, and then 1 by 12 is 12, and 3 times 16 is 48. The sum of which will give us 106. So we can say that the relative molecular mass of the compound Na2CO3 or sodium trioxocarbonate 4 is 106 with no units. 106 with no units. Sulfuric acid. I'm sure by now we understand the trick. So it's the same thing. 2 hydrogen atoms, 1 atom of sulfur, 4 atoms of oxygen. So we put it into the expression, generate our own expression, put the values or substitute the values into the expression, and we arrive at 98. 98. So compare it to your answers. Now, in the case of the compound I gave earlier, all right, I'm talking about the other compound, this one, the thiosulfate. Try it and give me your answer. So let's work it together. Try this one, because I didn't solve it here. I want to see your answer, and I'll be very glad to see your answer. So we'll do that of the sodium thiosulfate together. So let's do it together. We have the compound. Today we're having challenge with our equipment here. So we are going to calculate the molecular mass of sodium thiosulfate hexahydrate. All right, so with this, I multiply 2 by the mass of sodium, because in the compound, we have 2 sodium atoms, and then we add it to 2 by the mass of sulfur, but we have 2 sulfur atoms. Whatever we get, we add it to 3 by the mass of what? Oxygen, Ar, oxygen, because we have 3 of them. But if you check, there is a dot after the expression. Now, the dot indicates you have water molecules trapped in the crystal. It is part of the molecule, but has been separated because it's not part of the bond. So there are 6 of them. So we'll put 6 outside, get a square bracket, and then put into the square bracket 2 by the mass of oxygen. Sorry, 2 by the mass of hydrogen, because we have 2 hydrogen atoms. And whatever we get, we add it to 1 by the atomic mass of oxygen. I hope the expression is clear. So if you follow further, you see that this 6 will affect everything inside the expression, and then you will get an answer. Use this and give me your value. Okay. So we have also evaluated that of the copper 2 tetraoxide 6 decahydrate. So with this, just like we did earlier, we can also use this expression. We have one atom of carbon, so multiply 1 by carbon. We have one atom of sulfur, so multiply 1 by sulfur. We have 4 atoms of oxygen, so multiply 4 by that of oxygen, and then add it to 10 into bracket 2 times hydrogen, because in water we have just 2 hydrogen atoms, plus 1 times that of the oxygen. So what did you get for the first one? What was your answer for the first one? Kendra, what did you get? Kendra Hinkra. What was your answer for the thisulfate hexahydrate? Question number E. Unmute your mic. Hello, Kendra. Well, we can't hear Kendra, but we assume that you can all evaluate it. So you need a calculator to just do this if you can't do it offhand. So I give you time to work it out and then do your presentation. Like I said, you can send your answers to joylearningtv@myjoyonline.com. So you can send your answers there. We evaluate it and get back to you. All right. Remember to invite your friends and anybody around you, your church members or wherever you are living, to join us for the program. All right. So 12 o'clock every Saturday, there will be an interaction. All right. Teacher and you, so that you can learn more. Today we are having challenges with this machine. Henry, you are talking. We can't hear you. The line is breaking. So it's okay. You unmute your mic. Unmute your mic. We'll address it. We'll come back. We are having a challenge here, so we'll come back. My friends, we are having challenge with the internet, so bear with us, and we thank you for your patience. We want to push or advance the concept further to Avogadro's constants. Today we are having a lot of challenges with the screen. So we want to start with the mole. All this while, we were looking at the mole concept, the idea, all right, what we can use the idea to do. So we move on to what we call the mole. All right, the mole. What do we mean by the mole? In nature, there is an animal, in fact, a hairless rodent that lives in the soil. It is blind and it burrows its way through the soil. It is called a mole. That is not what we are talking about. And also, we know that sometimes in class or when we are with our friends and we decide to do bad things, most often bad things, one out of us will go and then report us to the authorities. We used to call them snitches. I'm sure you remember. Okay. They are also referred to as moles. We are not talking about those people. The mole here has something to do with the amount of substance present in a given mass of the carbon-12 isotope. This was first worked on by Avogadro somewhere in the 1860s. And today we are still using it. By definition, we say that it is the amount of substance equivalent to the number of elementary particles present in 12 grams of the carbon-12 isotope. So if you weigh 12 grams of the carbon-12, in any case, let's see by hands those who have seen carbon before. How does carbon look like? What is carbon? Yeah, I'm interested. So if you have an answer, you can unmute and then say it. All right, so Elba, go ahead. Tell us, what is carbon? Unmute and tell us. What is carbon? Elba, we are waiting. Carbon is ordinary charcoal. So the charcoal you see around is carbon. It's not any strange thing. It's not a wild element, okay? Carbon is charcoal, and the graphite in your pencil, the thing you use in writing from your pencil is also another form of carbon. Diamond is another type of carbon. So carbon exists in several forms. We call them allotropes in science. Carbon can be found in several forms. So you can have it in charcoal. Anytime you are burning your charcoal, remember you are burning carbon. When you are using your pencil, remember carbon. Myself and you, we are all made from what? Carbons. And then we also wear, I for one, I'm not a fan of jewelry, but diamond is really cherished by lots of people. All right. And there are other forms of carbons, like the nanotubes and the Buckminster fullerenes. These are forms of carbons we can find in nature. So if you weigh carbon, 12 grams of carbon, and you count the number of atoms in the carbon, you will get a number. And that number was first revealed by Avogadro. So later they named it after him. The number of elementary particles equivalent to what you find in the 12 grams of the carbon-12 isotope is what we call the mole. Is what we call the mole. The mole is denoted by N, small n, and it has the unit of MOL. Remember, it is a basic, in fact, it is a basic or a fundamental measurement. So it has the unit MOL and it is denoted by N. Today we are having challenges with our screen. Avogadro's constant, the man who worked and brought this out for us to be using today. So we recognize, we appreciate him wherever he is. May his soul rest in peace. Now, this is the elementary particles present in 1 mole of a substance. So that means that anytime we talk about 1 mole of a substance, it's equivalent to the number of particles in 12 grams of the carbon-12 isotope. The number of particles present in the carbon-12 isotope. And then the actual number of particles present there is what we call the Avogadro's constant. So the actual number or the elementary number of particles you can find in 1 mole of a substance is what we call the Avogadro's constant. Avogadro's constant is denoted by L, and it has a value of 6.02 times 10 to the power 23 entities per mole. If you have your calculator by you, let me show you where you can find it on your calculator. So if you have a calculator, pull it quickly. I'll give you some few seconds. So on your calculators. So if your calculator is on, go to Shift. Now, if you go to shift and you enter the number 7, so if you enter the number 7, it will give you a range of constants. For the normal calculators used by students, to give you from 0 to 40. So cross-check, you have 0 to 40. So on your calculator, you should have 0 to 40. Enter the number 24. The number 24. On your screen, I expect you to get something like Na, right? The old symbol used by Avogadro and the scientists of old was Na, and we are still using it. But because of the element sodium, we no longer use the Na. However, when it comes to electrical gadgets, we still use the Na. Enter the equal sign. So press on the equal sign. And when you press on the equal sign, you should get 6.02 times 10 to the power 20. In fact, it's going to be a very long decimal fraction times 10 to the power 23. Is that what you got? So shift 7, 24, and then enter. Now, if the calculator is yours, and maybe the cover is not missing, then you will have the range of constants also on the inner part of the cover. So check, you see a lot of values there. You have 0, 1, 0, 2, 0, 3, on and on and on. So the 0, 1, 0, 2, you see ME, MN, MP. The MP is not member of parliament. It means mass of proton. So you keep going on and on and on. All right. So with this, we can say that the actual number of particles you find in 12 grams of the carbon-12 isotope is 6.02 times 10 to the power 23. And we are using the word entities per mole. The word entities refers to the stable forms of matter. Matter exists in several forms, but the stable forms are the atoms, ions, molecules, human beings, stones, etc. All right. So we use the word entity. So it means that if they mention Avogadro's constant, they have this number of entities or this number of particles per mole of that substance. The number of entities in a substance. Let us look at this. You want to buy bread, and you want to know how many particles came together to form that giant loaf you have in your hand, you're about to consume. Let us see how we can calculate the particles, the number of particles there. The number of particles in that substance or in the bread is the total number of particles present in the bread. So you want to know how many particles came together to form the bread you are holding, that you are about to devour. From Avogadro's constant, we know that 1 mole of any substance should contain 6.02 on our screens, 6.02 times 10 to the power 23 entities. So if it is bread, 6.02 times 10 to the power 23 bread particles. All right, we are talking about flour and other things. But if you have 2 moles, it will be 2 times the Avogadro's constant. If you have 3 moles, it should be 3 times the Avogadro's constant. And similarly, if you have 4 moles, it keeps going on and on and on. So if we use an unknown amount or moles, which is the N, then it's going to be N times Avogadro's constant. I hope you are following. So we have N times Avogadro's constant. We can therefore generalize it and say that the total number of particles in the substance, so the total number of bread particles, will be the amount of the bread particles times Avogadro's constant. The amount there should be the amount in moles times the Avogadro's constant. Stretching the concept further, we can easily say that let N, capital N, be the number of particles in the substance, in this case our bread, and the amount in moles, and L, the Avogadro's constant. So if we want to find the total number of particles in a substance, for example, the bread, multiply the amount by the Avogadro's constant, and that gives you the value. All right. So if you want to find the total number of bread particles, all you need is the amount in moles, and then you can just multiply it by the Avogadro's constant. So this expression will help us do another type of calculation as we move further into the concept. Let us take an example, give ourselves a few seconds to digest it, and try to answer the question. The question reads, calculate the number of particles in the following. Calculate the number of particles in the following? I, 0.2 moles of oxygen molecules. I, 0.2 moles of oxygen molecules. I, 0.1 mole of ammonia molecules. I, 4.1 mole of gold atoms. 4.1 mole of gold atoms. And below the question, we have the Avogadro's constant. 6.02 times 10 to the power 23 entities per mole. If you are working with molecules, it becomes molecules per mole. If you are working with ions, it becomes ions per mole. And if you are dealing with atoms, you have atoms per mole. Any other entity you are talking about becomes that entity per mole. So I'll give you some time to work and then get back to us. Whilst we are working, I want to look at some of the comments that you have sent so that we can all discuss it. Okay, so let us look at the solution and compare it to what you have. I'm not going to call anybody. So those people who have run away, please come back. The network is worrying us today. I don't know why, but let's see what we will do. We can do. Our machine today is not moving very fast, and it's really affecting our class. Okay, so the question it has shifted. Okay, so for I, let n be the number of particles, and then small n amount in moles, and then capital L Avogadro's constant. So we can say that n there is, we are having a small challenge. We'll be back, please. The network is worrying us, so we can't get. It's not muting. I think it's a machine. The machine is slow. To reconnect. So you're welcome back to your Teacher and You on Joy Learning. And we are still continuing with the concept of what we call the mole concept. You can access this video online even after the session is over. You can access it on YouTube, all right, Facebook, understand other social media handles. So let's go back to the question that we were trying to solve. There was a question on board. They want to calculate the number of entities present in 0.2 mole of oxygen molecules, 0.1 mole of ammonia molecules, and 4.1 mole of the gold atoms. We're also given the relative atomic masses of, we're given the Avogadro's constant of the mole. Okay, so we said that let n be the number of particles, small n the amount in moles, and then the L, the Avogadro's constant. We said the total number of entities is given as amount in moles times the Avogadro's constant. So the solution to the first question. So in the case of the first question, L will take on the Avogadro's constant. Amount there will be 0.1. Using the expression capital N equals small n times L, we'll get 0.2 moles times 6.02 times 10 to the power 23 molecules per mole, of which the answer should be 1.204 times 10 to the power 23 molecules. So here you notice that the mole here has cancelled the per mole. We have A times A raised to the power minus 1. The answer is 1. That is why this has cancelled that, and we're only left with the molecule. So in the case of the second question, where L equals 6.02 times 10 to the power 23. If you substitute that one also into the expression, you get 6.02 times 10 to the power 23 molecules, all right, molecules. And then for the third question, where we're given 4.1 moles of the gold atoms, we follow the same procedure, and we are going to get 24.68 times 10 to the power 24, all right? Atoms, please change it because we are working with atoms. It should be atoms. This place should be atom, gold atoms. Atoms, all right? It should be atoms. So take note of that. All too soon, our class is coming to an end, but we cannot end the class without giving you a problem of the day or an assignment. So take this question down. Calculate the relative molecular mass of the compound NH4 Fe into bracket SO4 2. This compound is called ammonium ion 2 tetraoxosulfate 6. All right, ammonium ion 2 tetraoxosulfate 6. It's a compound that is used widely in the lab for redox titrations. And we have also been given their relative atomic masses as 14, 56, 32, and 60. So write the question. And then calculate the amount in moles in 4.11 times 10 to the power 22. All right, 4.11 times 10 to the power 22 molecules of chlorine gas. Molecules of chlorine gas. So if you are using your phone, you can take a screenshot quickly, and then you can solve it. The other end of the question, but I want to sign out by saying that today, the day has not been that very clean for us. We had challenges, and I want to apologize sincerely to you for starting late. And then we also want to encourage you to go online, go to YouTube. The video recording is there. Go to any other social media. You can get it there. And we want to sign up by saying that today we introduce ourselves to a very, very important topic in integrated science and chemistry, for that matter, the mole concept. We said it is an idea developed to determine the physical properties of very tiny substances, all right? And then it's dependent on the carbon-12 scale, the carbon-12 scale. And we said that the carbon-12 scale is a reference scale of 12 division, with each division representing a particle in the nucleus of the carbon-12 isotope. And we also mentioned that 112, the mass of one atom of the carbon-12 isotope, is also called the atomic mass unit, the atomic mass unit. And we said every element has its own unique relative atomic mass, and hence the value can be used to calculate the relative molecular mass. That is, when atoms combine to form compounds, we can put them together and get what we call the relative molecular mass, the relative molecular mass. We ended it by looking at Avogadro's constant, and then we've been able to calculate the amount in moles, as well as the total number of entities in a given substance. Share the video link, share the line with your friends, go to YouTube, and until the next time we meet, I want to say goodbye. But there is a quick information for you from my producer here. You can still go to, well, so a link has been dropped in the chat box. Please check. A link has been dropped in the chat box so that you can join the WhatsApp group. So share it with your friends. Right? The link has been dropped in the chat box so that you can share it with your friends. But if you have any question, you can go to Joy Learning TV at myjoyonline.com. Enjoy the rest of your weekend. Have fun.